Hey, welcome back. Today's topic is on 2D kinematics. In this section, you're going to define kinematics and dynamics, memorize 4 kinematics equations, and understand their differences. If you were to throw a ball as hard as you could from shoulder height in a perfectly horizontal direction, do you think it would take longer to reach the ground than if you dropped a ball from the same height? So dropping versus launching it horizontally, that would result in both balls falling at the same time. The overall concept for today's lesson is that the vertical motion is independent of the horizontal motion for an object being launched as a projectile. Let's review. Mechanics has 2 parts: kinematics, which is the study of motion without forces, and dynamics, which is the study of motion with the forces involved. We're going to use the same kinematics equations that we used in one-dimensional kinematics for two-dimensional kinematics. Because again, the vertical motion and the horizontal motion of a projectile, they are independent of one another. In your notes, define projectile, trajectory, launch velocity, and vector components. Basketballs, arrows, and bullets are among some objects that travel through the air in the same manner. When they're traveling through the air with the only force applied to them being gravity, they are called projectiles. If you toss a ball to someone, you probably notice that it doesn't travel in a straight line. The ball's path curves downward. This is why quarterbacks, dart players, and archers, they'll aim above their targets. Anything that's thrown or shot through the air is called a projectile, and because of Earth's gravitational pull and their own inertia, projectiles follow a curved path. Again, they have horizontal and vertical velocities, which are independent of one another. The path they follow is called the trajectory. When they launch, they have a launch velocity, and the launch velocity will be resolved into its x and y components so that we can use those kinematics equations to calculate other parameters of the motion. Let's do a little exercise to get you to understand projectile motion. In this section, analyze horizontal velocity and displacement separately from vertical velocity and displacement. The velocity is constant in the x direction. That means it does not change. Once the object is launched, it has a constant velocity in the x direction, also called horizontal velocity, because there are no other forces acting on it once it has been launched. No matter how hard you throw a ball, it leaves your hand at a certain velocity, and that stays constant. There is no acceleration in the x direction, so acceleration is 0 in those kinematics equations. Notice here, as a ball is launched horizontally, it is acted upon by the force of gravity in the vertical direction, but the horizontal motion shows a constant velocity where there are equal gaps and equal amounts of time in this diagram. Carrying on, let's start this exercise. If a ball leaves your hand with a velocity of 4 meters per second, and it takes 0.8 seconds to hit the ground, how far did it land from you? Well, 4 meters per second times 0.8 seconds gives me 3.2 meters. Another way to look at this is to use your kinematics equations. The final displacement equals the initial displacement plus velocity, constant velocity times time. Here's the constant velocity, here's time, and because the initial displacement is 0, we have final displacement equals 0 plus 4 meters per second times 0.8 seconds. So the final displacement is still 3.2 meters. This is just showing it in a different way using the formula. Let's see if you get this concept. If a toy car is traveling with a velocity of 4 meters per second and it takes 0.8 seconds to run into a wall, how far away was the wall? I'm going to draw 4 vectors, each equal to 1 meter. So the car has traveled 4 meters in 1 second. And it takes 0.8 seconds to run into the wall. How far away was the wall? Well, it is still 3.2 meters. It's the same as the ball above because, again, the horizontal velocities are independent of the vertical motion or vertical velocity. So even though a ball in part A is launched horizontally and it is falling, the horizontal motion is the same as if a car were driving on a flat road. Now let's throw the ball straight up in the air. If the ball leaves your hand with an initial velocity of 5 meters per second, and you catch it from the same height, velocity reaches 0 at the peak of the trajectory, comes back down. If you catch it from the same height, the final velocity is going to be negative 5 meters per second. How long was it in the air? Negative 5 meters per second equals 5 meters per second plus acceleration, negative 9.8 meters per second squared, times time. So we have negative 10.0 meters per second equals negative 9.8 meters per second squared times time. Divide by 9.8. And we are left with 1.02 seconds for time. Let's say you want to throw with a horizontal velocity of 4 meters per second and a vertical velocity of 5 meters per second. With what velocity does the ball leave your hand and at what angle? So when a ball is launched at an angle so that you can throw it across the room to your friend, it has two components. The first component is the horizontal component, and it gives us 4 meters per second for that. And the second component is the vertical component. Notice I'm making a right triangle. The vertical component of the velocity is 5 meters per second. We want to know with what velocity the ball leaves your hand and with what angle. So velocity has two parts, speed and direction. The direction in this case will be the angle. So this is launch velocity, this question mark. So you use the Pythagorean theorem to solve for the hypotenuse of this triangle we just drew. 5 squared plus 4 squared is going to equal c squared. That's a squared plus b squared equals c squared. 25 plus 16 gives me 41. I'm going to have meters squared per second squared equal to c squared. If I take the square root of both now, I end up with 6.4 meters per second equal to c, which is our launch velocity. Now we need an angle. Remember from math, you learned SOHCAHTOA. And I'm going to use two values that are given, rather than my 6.4, which I calculated, because if I made an error calculating 6.4, I don't want to make a second error calculating the angle. So I'm going to use tangent, or tangent TOA. Tangent of angle theta will equal the opposite side, so here's angle theta, and the opposite side is 5, over the adjacent side. The adjacent side is connected to the angle, that is 4. And I'm going to get theta by itself, I have to take the inverse tangent. So that's tangent negative 1 on the calculator. You'll see a key for that, of 5 over 4. That's going to give me an angle of 51 degrees. And make sure your calculator is in degree mode, not radians. If it is in radians, you'll have a decimal number. That should be a red flag to you to change the mode to degrees. All right, so our launch velocity is 6.4 meters per second at 51 degrees above the horizontal. E, your friend catches it at the same height 1.02 seconds later. How far away is she? So it goes up and it comes back down and it lands at the same height. We want to know how far away she is. Well, we know the speed, the horizontal speed, and we know the time. So just like the car running into the wall problem or launching a ball horizontally, you can take your speed, that's velocity, times your time, and you'll get 4.08 meters. Seconds cancels, you're left with meters. Remember, that stems from the final displacement equals the initial displacement plus velocity times time, which is here, where initial displacement is 0. How long was the ball in the air? Well, that was given to us 1.02 seconds. G, what was the maximum height of the ball? We know that at the maximum height, the final velocity in the y, or the vertical, is going to equal 0 when the ball is at the peak of its trajectory. The initial velocity is going to be the one that's in the y direction, not the x direction, and not the one at the angle. We want to use the vertical component of the velocity, and that was 5. When we're working in the vertical direction, we only want to use the vertical components. So acceleration is acting vertically, and that is going to be negative 9.8 meters per second squared. And if the flight time of the ball was 1.02 seconds, then to reach max height, we're going to take half of that, or 0.5 seconds. So time equals 0.5 seconds. Okay, let's use the position function. The final displacement in the y, okay, because we want height. It's going to equal the initial displacement in the y, which is 0, plus the initial velocity in the y, which was 5 meters per second, times the time, half a second to rise, plus 1/2 times negative 9.8 meters per second squared, times the rise time, 0.5 squared. Don't forget to square your time. That's the most common mistake students make. When you calculate all of that, you should get 1.28 meters. H, which of the 4 components of projectile motion is identical in both the horizontal and vertical calculations? That's going to be time. Explain the difference between horizontal and vertical displacement. The horizontal is range, and the vertical displacement is called height. J, explain the difference between horizontal and vertical initial velocities. The horizontal velocity is constant, so whatever the initial velocity is, it does not change. And the vertical velocity does change based on the acceleration of gravity. Changes due to gravity. Okay, explain the difference between horizontal and vertical acceleration. The horizontal acceleration is 0, there is none. The vertical acceleration is g, or acceleration due to gravity, and that's going to be negative 9.8 meters per second squared. It could be positive if you decide the ground direction is positive. Okay, key concepts. In this section, you're going to determine the factors that affect trajectory. Does mass affect trajectory? Take a tennis ball and a ping pong ball and push them off the edge of the table using a book so that they leave the table at equal times. Ideally, you would have 2 spheres of the same diameter, one with more mass than the other, but we'll work with what we've got. Predict which ball will hit the floor first. Make your prediction now. What do you think? Let's find out. Also predict which one lands farther away as measured from the leg of the desk along the floor to the ball. Explain your predictions, then test it. So, do you think mass affects motion? Is mass a factor for any of the projectile motion equations? If you haven't done so, pause this video, do the demo, and then come back to check your answers. Pause it now. Welcome back. Which ball hit the floor first? Well, in an ideal situation, they hit at the same time. Which one lands farther away as measured from the leg of the desk along the floor? Well, if you're pushing with the same force, what do you think you would get? The little one should move farther away. It would take more force to launch the more massive ball, but we'll talk about that in the next section. Does mass affect the motion? No. Is mass a factor in any of the projectile motion equations? No. So with this said, an elephant and a mouse are dropped from a parachute and they splat on the ground at the very same time. And this is neglecting air resistance. So basically, if they were both dropped from a airplane in the vacuum of space where there was no air, they'd probably suffocate before they, actually reach the ground. But anywho, they hit the ground at the same time. How is the horizontal motion connected to the vertical motion? As we discussed before, that is the one component that is time. How is the horizontal motion separate from the vertical motion? Well, they're independent of each other, and that's why we do separate calculations for vertical motion and horizontal motion. Imagine standing behind someone who's tossing a basketball into the air, into the hoop away from them. What path do you see? Well, you just see the ball go up and down. But if you're standing on the sideline, you're going to see a parabola. So again, motion in the x and y directions are completely independent of one another. Note the trajectory of the ball given an initial horizontal velocity versus one dropped. So what is similar about the two paths? This one is given an initial horizontal velocity, which is constant. And this one is dropped, so its initial velocity is 0. Let's call this one 5 meters per second. We'll go with 4 because that's what we've been working with for the previous problems. So you can see here that the acceleration due to gravity acts on them in the same manner. Okay, so describe the vertical motion for each. They accelerate at the same rate, gravity 9.8 meters per second squared. Describe the horizontal motion for each. The first one has no horizontal motion. And the second one moves forward. With a constant speed. Here are separate motion diagrams for the vertical and horizontal motions shown by the balls in the previous example. There is acceleration in the y direction due to gravity. The x and y components can be used to get the resultant vector at each step. Notice the resultant forms a parabola. So if we look at B here, we have vertical motion. The velocity is increasing with the acceleration of gravity. So if we combine this with the horizontal motion, we get the resultant. And as we line these up, you're going to see half of a parabola here. Here are tips for solving kinematics problems. Divide the problem into x and y portions. The y component is only acted upon by gravity. When an object is dropped, its initial velocity in the y is 0. When tossed up, there is a velocity in the y direction, and the peak velocity is 0. At the peak of the trajectory, the velocity is 0. 4, the x component has no acceleration or gravity. 5, the x velocity is constant. It is the same throughout the motion. 6, x and y directions are connected through time, so time is interchangeable between the equations. Remember, if you want to find half of the trajectory, you use half of the time. How far is also called range. That's the horizontal displacement. Okay, let's do a class example. Label this horizontal launches and show the work in your science notebook. A stone is thrown horizontally at a speed of 5 meters per second from the top of a cliff that is 78.4 meters high. Draw this picture. How long does it take the stone to reach the bottom of the cliff? You want to divide up your parameters into x and y. So here I have x. Notice I only have one variable in the x direction. I can't solve anything with that. You need two or more variables to solve any part of the equation. So I'm going to work in the y direction to find how long or how much time it takes the stone to reach the bottom of the cliff. So I need to find time. My final displacement, I'm going to use the position function. This is initial velocity in the y times time plus 1/2 at squared. The final displacement is 0. The initial displacement is 78.4 meters plus initial velocity in the y. It's as if the stone is being dropped because it's not being propelled upward or downward. So the initial velocity in the y is 0. 0 times time is still 0. Plus 1/2, negative 9.8 meters per second squared times time squared. I'm going to move my 78.4 to the left side. Half of negative 9.8 is negative 4.9 meters per second squared times time squared. Divide by negative 4.9 on both sides. Let's crunch those numbers. Negative 78.4 divided by negative 9.8 gives me 8. Meters divided by meters per second squared gives me seconds squared. Okay, now you need to take the square root of both sides. And I get 2.8 seconds. Yeah, I calculated that wrong. Why did I plug in 9.8? It's negative 78.4 divided by negative 4.9. I already took the half of that. Here we go, 16. Square root of 16 is what we want, and that's going to give me 4 seconds. Okay, 4 seconds, final answer. What is the horizontal displacement of the stone? Okay, so remember, the time is used for both the x and the y direction. So now we know time in the x direction as well. It's for both. So we know the time is 4 seconds to fall and hit the ground. So if the initial velocity in the x is 5 and it moves for 4 seconds, then our displacement or range is 20. That's constant times time. 5. Four seconds. So final displacement, and this is in the x direction. Don't get that mixed up. Again, you can't mix and match x and y parameters. What are the horizontal and vertical components of velocity when the rock hits the ground? The x component is still going to be the same. Velocity in the x does not change, so that was 5.0 meters per second. We want to know, because it's speeding up, we want to know the final velocity in the y. So final velocity in the y direction is going to equal the initial velocity in the y direction plus acceleration times time. So v final in the y equals initial velocity in the y. Again, the ball is being launched horizontally, so there is no vertical velocity. It's as if the ball is being dropped vertically. and it takes 4 seconds to fall. So what we have here is acceleration times time. So -10 times 4 is about -40, or 39.2 meters per second downward. So those are the components, x and y. Okay, check Schoology for the problem set you'll be working on. And let's do 2 more examples. We're going to see how time is connected between the x and y direction. All right, toy giraffes are being sent down a conveyor belt. At the end of the belt, they go horizontally off the edge. Where's my pen? There it is. They go horizontally off the edge and land in a box that is 0.6 meters below. I'm going to draw my y-axis here, my x-axis. This marks 0.6 meters. I'm going to mark the ground as 0 meters. And it says that they land 0.4 meters away. Now instead of putting time here, I'm just going to put 0.4 meters for horizontal displacement. What is the horizontal velocity of the giraffes as they leave the conveyor belt? So velocity in the x equals a question mark. Okay, divide your problem into x and y components. Velocity in the x, we don't know. Initial velocity in the y, we do know. It's as if the giraffes are being dropped, so that is 0. Final velocity in the y, we don't know. Time, unknown. Acceleration, here now we're getting somewhere. So I know 2 parameters in the y I can solve. This is x, this is my y side. I'm going to go ahead and find time. The final velocity in the y equals the initial velocity in the y direction plus acceleration times time. The final velocity, oh, we don't know final velocity. I can't use this equation. I can use position. I know the positions. D final in the y equals 0 and D initial in the y equals 0.6 meters. So I want to show you that students come across this problem all the time. They start using an equation and find out, hey, I have 2 unknowns. I can't use this equation. So you want to pick the equation where you only have 1 unknown. Using the position function, final displacement in the y is 0. Initial is 0.6 meters. Initial velocity in the y is 0. Plus 1/2 times -9.8 meters per second squared times time squared, and time is going to equal 0.35 seconds. Don't forget to square your time and take the square root at the end. Now I want to know what is the horizontal velocity. Okay, so if I know time and I know the range, I can find that horizontal velocity. Final displacement in the x equals initial displacement in the x plus velocity in the x times time. Velocity in the x times 0.35 seconds. Initial displacement is 0 and final is 0.4 meters. 0.4 meters divided by 0.35 seconds equals velocity in the x, where velocity in the x equals 1.14 meters per second.